Session, but we'll start with a talk by Hayder Salman about solitons, breathers, and superfluid vortices.
Thank you. Well, first of all, I'd like to thank the organizers for the opportunity to talk here today. Now, this talk is going to be related to ideas from superfluids, classical fluids, and it also is going to bring in ideas from integrable systems to try and uncover novel vortex dynamics that I believe have been overlooked thus far in the context of superfluidity in particular. So in way of motivation, I'd just like to remind you that topological defects arise in superfluids in the form of quantized vortices, where the circulation is quantized. And what I'm going to be really focusing on are 3D vortex structures. And we have already heard people talk about the possibility of having excitations in the form of Kelvin waves propagating along these vortices. And these Kelvin waves are essentially helical-like disturbances. And if you perform some kind of linear analysis on the problem, you obtain a dispersion relation that tells you that the phase speed of these waves is related to wave number, and so you have dispersive excitations, essentially. Now, most of this analytical analysis is typically done in the context of linear analysis, but I'm going to be interested more in high amplitude excitations, nonlinear excitations, because it's relevant, in my opinion, to study of solitons on these vortex filaments. And in particular, I want to focus on these breather solutions, as they're called. Unlike solitons, where you can always find a frame of reference, at least for a single soliton, where if you move in that frame of reference, the soliton appears stationary, breathers are really unsteady solutions. And unlike solitons, they are localized in both space and time. And in fact, they have been invoked in recent times to, as models of so-called freak or rogue wave events in the ocean. And the main message that I want you to take from my talk is that these kind of freak or rogue waves, so this is an example of a pyramidal freak wave. This is another one, essentially a wall of water approaching this vessel here. What I want you to take from this talk, essentially, is that this kind of phenomena is a manifestation of the same kind of process that leads to this kind of structure on a tornado. In fact, I had to dig hard through the literature to find this photograph that was in one of Hassan Aref's papers in JFM. And it's interesting to see that you have this kind of loop-like structure that you see on a tornado. Right, so let's proceed. So we already heard that these vortices can be modeled through the Biot-Savart law, where the velocity of points on the vortex filament evolve according to this non-local integral. And it turns out that this description is a very good description for superfluids, provided the vortices are well separated or the radius of curvature is much larger than the healing length, in which case compressibility effects become less important, and then this model for an incompressible vortex is a suitable description. Now, if you try to describe the leading order dynamics of the motion of this filament by doing essentially a Taylor expansion around the point you're considering, then you obtain the so-called local induction approximation, which tells you that the motion of the point on the filament will move in the binormal direction at a speed that's related to the local curvature. Now, this is a severe truncation of the vortex motion, but nevertheless, it's interesting because in 1972, Hashimoto pointed out that there is a transformation that links these two descriptions, the local induction approximation and the nonlinear Schrödinger equation. And essentially, if you take a filament, which can be described in terms of the Serre-Frenet equations that relates the tangent, normal, and binormal to the curvature of the filament and the torsion of the filament, so these are essentially the intrinsic variables for a vortex filament, then you can introduce a complex function phi such that its amplitude is related to the curvature. The derivative of the argument with respect to arc length is the torsion. And so from that, you can show that there is this correspondence with the nonlinear Schrödinger equation, which is a 1D nonlinear Schrödinger equation as shown here. And what's interesting is that since this is a nonlinear Schrödinger equation in 1D, then you immediately expect it to be integrable, so you expect to have soliton-like solutions for this problem, and Hashimoto realized this, and he went to identify 3 types of solitons, a so-called hump, cusp, and loop soliton. So I'm showing examples of 2 of them here. So this is a hump soliton where you see a localized disturbance on the vortex filament from a front view and a side view, and the loop soliton is shown here, which appears to self-intersect, but of course it just arises from a non-single valuedness of the function when taken along the axis of the vortex. Now, Aref actually suggested that this loop that you saw in the tornado could be related to these loop solitons, and what I want to propose is that this is probably a manifestation of another type of solution, which is the so-called breather solution. Now, breathers, I mean, some of you will be familiar with them, but I think they are less known than soliton solutions because they require additional conditions. So first of all, they have been confirmed experimentally only recently. So in the last 3 years, in fact, they've been found to exist in experiments. But moreover, they need an additional condition that the dispersive term and the nonlinear term have to act to reinforce one another to get this kind of breather behavior. So there are several breather solutions derived as far back as I think the 70s and 80s. One of them I'll be interested in here is the Akhmediev breather solution, which is shown by this expression. So essentially what you have is this kind of plane wave, a spatially uniform plane wave with a modulation given by this term. And you see that the modulation reaches its maximum value when t is 0, and it has this spatially periodic structure because of the cosine terms where the arc length appears. And it reaches a maximum amplitude given by this expression at t equals 0. There's another type of breather which I will not be too concerned with, but I just want to point out that it's essentially where the roles of space and time are reversed. So it's a temporally periodic solution with a spatial modulation. And in the limiting case, where the temporal period or the spatial period of these 2 breather solutions tends to infinity, you recover what's called the peregrine soliton, which has been introduced as a prototype of freak waves in the ocean, which is shown by this expression here. Now, as I said, these solutions were predicted a long time ago, but it was only recently in the context of nonlinear fiber optics that some of these solutions have been confirmed to exist. And since then, there have been additional confirmation in other contexts, for example, surface waves. Now, just to give you an interpretation how you should think of these breather solutions, if you think of a dynamical systems argument for analyzing fixed points, you can have a saddle point, for example, in a dynamical system, where it has an unstable trajectory that emanates from the fixed point and then approaches the fixed point from a different direction. So this is what's called a homoclinic orbit. And these breathers have been essentially explained as an analog of these homoclinic orbits, but for partial differential equations. So in other words, infinite dimensional dynamical systems now, where the trajectory departs from some stable solution and then approaches it from another direction. And they're quite generic, arising in other equations, for example, in the nonlinear Klein-Gordon equation, which we have heard in the last couple of days can be used to describe other systems, such as cosmic strings and so forth. Right, now I'm going to focus on the Akhmediev breather, and the first thing is that this modulation here is on a plane wave that's spatially uniform, which means that you have 0 torsion and constant curvature. And what I want is to consider the case of a helical vortex, which have non-zero torsion and non-zero curvature. So this is the first obstacle I had to overcome. And this turns out to be quite straightforward because there is, well, we can use properties of the nonlinear Schrödinger equation, which is known to be Galilean invariant and scale invariant under these 2 transformations. So by doing a gauge transformation of this form, you can bring in a dependence on the torsion. And likewise, you can modify the curvature of the filament through this transformation. So if you have a breather solution, it transforms into either this or this, depending which of these transformations you introduce. And so you recover a solution that's homoclinic to a helical vortex filament. Okay, so this is a bit technical, so let me show you some examples. So this is a result in the local induction approximation context, where you see a vortex filament evolving, undergoes an instability essentially, leads to these very large loops, which are the vortex analogs of these freak waves, and then relaxes as the modulation decays. I want to stress that actually this feature doesn't only arise when you have high amplitude disturbances. It can arise even when you have low amplitude disturbances. So if you consider, for example, this very low amplitude disturbance here, after some time, this is looking at it from a side view, this is from a front view, you see that a disturbance, a localized disturbance still arises. And so this, of course, can be relevant also in the context of Kelvin waves, where you're essentially in this regime of low amplitude excitation. So this instability is always present in the system. Okay, how does this relate to the full vortex dynamics when you have the Biot-Savart description? So I'm going to show you now simulations where we've taken a vortex filament with a hump soliton and a loop soliton, and we're going to see how they interact under the full Biot-Savart dynamics. And if we animate this, then you see that the solitons move close together. Eventually, they interact, and then a reconnection takes place. So the important point is that the initial disturbances do not disperse. So they do continue to act as solitons at initial times, and eventually integrability is broken through a reconnection. So given that these predictions from the local induction survive under the full Biot-Savart dynamics, then it was, of course, natural to consider what will happen with the breather solution and the full Biot-Savart dynamics. And again, you see this instability eventually leads to a pinch-off of the vortices. Loops are generated and emitted, and you get these sort of Kelvin waves produced. Okay, so what about something a bit more realistic, a mean field description of a superfluid? So we have already heard that a good model, a good microscopic model for a superfluid is the Gross-Pitayevsky equation, which essentially describes, provides a mean field description of a macroscopic condensate wave function given by the complex field psi. And through the Madelung transformation, you can map this onto fluid mechanical equations. And so you expect to be able to model vortices with this GP equation. And the main advantage of working with this equation is, of course, the quantization condition emerges naturally. You do not have to impose it explicitly, as in, for example, in a Biot-Savart description. And so you have the full description, including phonons, compressibility effects, vortex dynamics, and so forth. So we initialized this the GP model with this initial condition, where you see that you have a winding of the phase. So there's a jump in the phase here to give you the circulation. And then we looked at what happens to this structure under the full Biot-Savart equation with the same initial condition. And as before, the structure persists and leads to this pinching off. So these structures that are predicted from simple local induction approximation arguments do survive under the full mean field description as well as the Biot-Savart law. How am I doing for time, actually? Okay. Right, so these structures are quite generic. And I wanted to draw an analogy now with an instability that actually was discovered a long time ago in the 1960s in the context of surface waves and fluids, which is the so-called Benjamin-Fehr instability. Now, this is essentially a modulational type of instability. And if you linearize the equations and look at the dispersion relation, you find that for long wave numbers, for long waves, so low wave numbers, you have unstable modes in your system. So you can recover this instability provided you have a large enough computational box that you can capture these unstable modes, or equivalently, you need large amplitude perturbations. It turns out that as you make the perturbations or the base state, the helical wave with lower amplitude, then you need a larger and larger box size. So if you're, for example, interested in the regime where Kelvin wave turbulence is dominant, then you need a very large box to be able to see this instability. But it's there nevertheless. So how does this relate, for example, to some of the questions on superfluid turbulence? We've heard quite a bit being said about that in this meeting. And so I just want to say that, I mean, superfluid turbulence is actually a very difficult problem, and there's very little understood about it, even when it comes to understanding basic questions such as how energy is dissipated in the system. Now, there are several regimes that have been identified and proposed in the process of dissipating energy in superfluid turbulence. So we've heard, for example, that at large scales, you have a quasi-classical-like regime where vortices are polarized and they move together and they mimic kind of eddies in classical turbulence, and you get a Kolmogorov-like spectrum. At very small scales or high wave numbers, the main mechanism is believed to be the Kelvin wave cascade, where essentially these Kelvin waves with different wave numbers undergo kinetic interactions. In fact, you can analyze the problem quite analytically in that case by deriving a set of kinetic equations and recover some spectra. But there is a problem of how to match the two descriptions together, because the energy flux predicted at low wave numbers or large scales does not seem to match with what can be carried by the Kelvin wave cascades, which is argued to eventually lead to phonon emission. So there is this problem of how to match the two regimes. Now, if we entertain the possibility that energy comes down from the larger scales and begins to pile up because there isn't a simple route for it to go to higher and higher wave numbers, then you can expect this energy is going to be stored up essentially in large amplitude perturbations. And these large amplitude perturbations will lead to self-reconnections and vortex ring emission. So what I've done here is I've considered a slightly sort of hypothetical scenario where I have a strongly bond vortex with many wavelengths on it, and considered how this instability affects the evolution of this vortex. And you see the instability immediately leads to a very complicated vortex motion where the vortex undergoes, well, essentially almost disintegrating into lots of vortex rings and loops. And so this instability seems to play an important role in the dynamics at these well, what I believe are to be these sort of intermediate scales where the excitations on individual vortices are still very large, so before the Kelvin wave cascade has kicked in. And so with that, I think I'll end here by saying that we've shown that there is this correspondence between the local induction approximation and the self-focusing 1D nonlinear Schrodinger equation, where we've been able to identify these briefer solutions. And the important thing is that these predictions from this simple model seem to persist under the full Biot-Savart dynamics and a mean field model based on the GP equation. So they are essentially nonlinear extensions of unstable modes of your helical vortex filament, and I think that this can have consequences, for example, on the question of the Kelvin wave regime, since you are essentially dealing with these well, since these this instability can have an effect on the spectra that you see. In fact, it's been a very contentious issue of how of what the spectrum should be in superfluid turbulence, and numerical calculations have not converged on any result. And perhaps this instability is one reason why it's difficult to identify what the spectrum should be. I also want to point out that given some of the things that I've seen in the last 2 days, it seems to me that there are analogs of this instability that must exist in other contexts, perhaps in cosmological strengths or defects in other condensed matter systems, and it would be interesting to explore these other connections. So, thank you.
Questions?
Yes. You know, in water wave theory, in the context of also 1D models, right? So this modulation instability was also discussed by Benjamin Fair, as you mentioned. And people introduce so-called Benjamin Fair index. Benjamin Fair as name of instability.
Okay.
So basically, which measures what process dominates? Is it modulation instability or resonant wave interaction, like in wave turbulence? So essentially, if the spectrum is broad, then resonant interaction wins. right? If it is narrow spectrum or almost monochromatic, then modulation instability wins. And so basically there is a measure that is a ratio of the two that seem to work very well. And that's been validated on, people like Miguel Honorato using exactly 1D NLS model. So that might answer the question, what role you have of this instability versus, say, the wave kinetic process. So it depends on the forcing or the initial spectrum you have, whether it's broad and strongly nonlinear or other way around.
Yeah, I mean, I think there are two issues here. I mean, one is in terms of the balance of the different effects. But the other thing I think that one needs to keep in mind is that to get to the Kelvin wave cascade, these large amplitude perturbations have to decay so that you are in the Kelvin wave regime. And before you actually get there, the instability might already kick in and modify the geometry of the vortex significantly. And so it's not clear that whether you eventually end up with a sort of this clean kind of Kelvin wave cascade, or whether the instability will have kind of distorted the vortex significantly before you get there. So that's another effect in addition, I think, to the one.
Sure, but even for strong nonlinear waves, for this instability to work efficiently, you should have narrow spectrum. So like in your wave train that you showed, it's almost monochromatic.
In the example you showed, a picture taken from SNRF is an example of vortex breakdown. This is what happens for vortex in a normal fluid when the stretching is reduced locally. So this is a sort of generic process. Would that be a new approach? I mean, vortex breakdown is a very confusing, confusing data about it. So could this be a new approach to it?
Well, I actually would sort of distinguish it slightly from vortex breakdown. I mean, I tend to think of vortex breakdown as where you have adverse, perhaps pressure gradient effects with sort of slow down the flow. I mean, here, this is, I think, something different. So while it seems like it looks similar visually to vortex breakdown, I do think it's different dynamics that's at play here.
So when integrability is broken, some of the conservative quantities for nonlinear Schrödinger equation is not conserved, I think. And
well, I mean, essentially, for example, in GP model is a Hamiltonian system.
yeah.
So essentially, you have exchange between kinetic energy of vortices and energy due to sound emission, which is, of course, I mean, there will be this exchange of energy. So the integrability of the vortex is so if you're working within the concept of the GP model,
geometrical constraint like the total length or something else.
Length of the vortex filament.
Yeah.
The length is not conserved under the Biot-Savart law anyway, even without reconnections. So.
Okay, well, thank you again.